Welcome to the video summary series for Pedisco's Introductory Statistics textbook. In addition to chapter summary videos such as this one, Introductory Statistics also offers podcasts, virtual tutor e-learning, homework activities with anti-cheat and auto-grade functionality, and detailed instructor resources. Find out more at pedisco.com/introstats. For now, over to the author.
Hi again, I'm Sean Thompson and welcome to the next video in the Pedisco Introductory Statistics video series. In this video we'll be talking about regression. To start off, pretty soon I'll be talking about regression fundamentals, then I'll move on to the formal simple linear regression model, and I'll finish up with a look at multiple regression. But as a very first point, let's ask ourselves, what is regression? Well, often we'll be in a situation where we want to know what value a variable is going to assume, but for various reasons it might not be as simple as simply measuring that variable. For example, maybe the value we want to know is going to occur in the future, or maybe the variable is just hard to measure. In situations like this, we'd like to be able to model the variable's behaviour with one or more other variables. And this is what regression is all about. Now, because of this, what we'll find is that we'll be looking at the relationships between variables quite a bit. So at this point, I'll point out that the earlier chapters of the Pedisco textbook go into detail about how to describe the relationship between data from two variables. There's also a summary in the regression chapter on all of the relevant stuff. Remember that a scatter plot is a good way of drawing these sorts of relationships, and the correlation between two sets of data is a number that indicates how strong the linear relationship is between the two data sets, and the line of best fit is a linear equation that represents a line that goes through the scatter plot. The idea is that it is a line that numerically describes the linear relationship between the two data sets, assuming there is one. But everything I've just mentioned is about describing relationships. Regression is about using these relationships to make predictions. So let's go there. We'll start with regression fundamentals. For now, we'll assume we are in the situation where we will use one variable called the explanatory variable, and often denoted x, to model the behaviour of another variable called the response variable, and denoted y. And we'll assume that the model is based on a linear relationship. For example, we might want to model how much a house will be sold for on the market based on the number of square feet in the house. So the square footage of the house is the explanatory variable, and the house market price is the response variable. And we are assuming that we can effectively model one on the other with a linear relationship. So how do we go about building such a model? Well, through data. For example, you might go out and collect data for 100 houses that have been sold recently. For each house, you measure the square footage and the sale price. Let's suppose this relationship looks like this for your data. So that's great, that's a description of the relationship, but how do we use this? What's the model? Well, the model is actually just the line of best fit. So that line there, or more accurately the equation for that line, is pretty much the most important thing in this whole video. It's the regression model. Now, in the context of regression, we write the equation like this. The fact that there is a little hat on the y in that equation means that we are using this equation to come up with a predicted value for the variable y. We plug in a value for the explanatory variable, that's the little x, and that, together with the two constants, b0 and b1, produce a predicted value, y hat, for the response variable. For example, the data in the house example might produce a line of best fit with this equation. In regression, we call this line the regression line. Now notice that in the sample there is usually a difference between the observed value for the response variable and the value predicted by the regression line. Let's just take one point for example. If a house is 500 square feet, this regression analysis would predict that the house would sell for $450,000. But look, in the data there was a house that was 500 square feet but it sold for $490,000. Now, there's nothing to worry about here. Of course, the model is not perfect. No one was ever pretending it was. But these observed differences are known as residuals, and the amount that these residuals vary does give you an indication of how precisely you can use your regression model to predict the response variable. That's because they feature in a thing called the prediction interval. As we just saw, a house of 500 square feet is predicted to sell for $450,000. But also, as we just saw, this single value prediction is often going to be not quite right. Now, just to repeat, that's okay. No one ever pretended that knowing the number of square feet in your home is going to tell you exactly how much it will sell for. It's okay that the regression model isn't perfect, but one thing we can do when we get a predicted value is we can measure how precise we expect that prediction to be. And we do this with the prediction interval. So you'll get your predicted value for y, but you'll also get a margin of error around that predicted value. And the formula for the prediction interval is fairly complex, but it does involve those residuals I was just mentioning. And the formula is given here. Statistical software will often help you calculate the interval, so as per usual, the important thing to be able to do is to interpret the interval. For example, you might find that if a house has 500 square feet, the 95% prediction interval for the selling price of that house is $450,000 plus or minus $100,000. And that means that 95% of homes with 500 square feet will sell for somewhere within that range. Now, I'll just briefly show you the formal simple linear regression model. And by the formal model, what I mean is that the regression line that we've just seen is a sample line that takes in a value of x and spits out a predicted value of y. It's very useful, and it's what you'll mostly use in your regression analysis, but where does it come from? Well, technically speaking, we have to address this fact that even when you have a fixed value of the explanatory variable, like a 500 square foot home, for example, your response variable is going to vary. Technically speaking, the regression model is based on the idea that at each level of the explanatory variable x, the response variable y is a random variable, and the expected value of y will follow a linear relationship with x. The best way to represent this idea is to say that y and x exist in a relationship like the one presented here. In that equation, beta 0 and beta 1 are constants. In fact, they're parameters that correspond to the sample statistics b0 and b1. But the epsilon is a random variable, and that's what allows y to vary about the regression line. While you don't technically use this model in a practical sense, for example, you rarely know the true values of beta 0 and beta 1, it's good to know the formal model underlying what we do. The Pedisco textbook goes into much greater detail on estimates and tests that you can conduct regarding this model, so go there to have a look at that. I'll finish up now with a little introduction to multiple regression. So what do we mean by multiple regression? Well, in all regression, we're only ever trying to predict a single response variable. But there's no limit to the number of explanatory variables we can use to do that predicting. In fact, the more explanatory variables you use, the more information you have, and the better your prediction is going to generally be. For example, to predict the selling price of a house, we might take into account its square feet, but we might also take into account the number of bedrooms in the house, for example. So a multiple regression equation with two explanatory variables will look like this. Notice that it looks a fair bit like the regression line earlier, except now there is another x value tacked on the end. And this value has its own coefficient as well, b2. But other than that, we use the equation in a very similar way. Let's see an example in a question from the Pedisco workbook. In this question, Eastpak Bank has developed a model to predict the probability that a person will default on their mortgage. This model takes into account two explanatory variables, the age of the person and their annual income. The regression model that the bank developed is given here. Now, the bank is looking at a person who is 39 years old and earns $53,000 a year. What is the predicted probability that they'll default on their mortgage? Well, you just plug the values of the explanatory variables into the regression equation, which I did earlier, and you get your predicted value. And notice that we get personalised feedback and an explanation of the question. So that was regression. The key topics were regression fundamentals, the simple linear regression model, and multiple regression.